Okay, so for this demonstration, come grab a book.
Okay.
All right, and we need a bowling ball as well. So let's put the bowling ball on the ground. All right, so the way this is going to work is I'm going to start the bowling ball right here. And I'm going to roll the bowling ball that way. And what I want you to do is, in one whack, I want you to cause the bowling ball to speed up but not change its direction. You ready?
Yeah.
Okay, here we go. Okay, what way did you push it? Same direction it's going. All right, send the bowling ball back. All right, same thing. This time I want you to slow the ball down but not change its direction. Okay, ready? Here we go.
I don't think that worked.
Okay.
It slowed it down.
Which way did you push it?
That way.
Push it, so you push it the opposite direction it's moving.
Yeah.
All right. This time I want you to neither speed the ball up nor slow the ball down, but I want you to change the ball's direction.
Okay.
Okay, you ready?
That's
Here we go. You know what you're going to do?
Sort of.
Sort of. What are you going to do?
I'm just going to let it hit off the book and go off that way.
Okay, so which way are you going to push?
oh well.
That way.
So pushing in the direction it's moving will speed it up.
Yeah.
Pushing opposite the direction it's moving will slow it down.
You push it that oh, but it won't work.
So I don't want you to push it in or opposite the direction.
To the side. Then.
Ah, to the side. Okay, here we go. All right. Got it? All right. So that is the basic idea. Is the ball accelerating?
Yes.
Yeah.
Yeah, is it speeding up?
No.
No, it's not speeding up or slowing down, but it is accelerating because its velocity is changing. Wouldn't you agree?
Yes.
Okay. So we're going to play a little game, and we'll see how good you guys are. And we'll compare you to 7th period to see who's better. So what I need is we have a total of 8 books. I need whoever wants to play, go grab a book.
Yes, so
All right, so I need one person to stand back where Jack is. All right, Sean, okay, stand there. Justin, stand directly across from Sean. Okay, so how many squares apart are you? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so I need somebody to stand about 1, 2, 3, 4, 5 squares back, halfway in between these two guys. And then 1, 2, 3, 4, 5 squares back. You've done this before, so you should know. All right, and then, okay, so we've got kind of a diamond right now, and then we need people spaced in between to form a circle. Okay, there are 2 people there and 0 people here. All right. Okay, good. So you probably want to move forward just a touch, move backward just a touch. All right. So we're forming as close to a perfect octagon as we can. So the goal of this game is I'm going to launch the ball in from the side, and I want you to make the ball go around in a circle, or I guess an octagon, right? Go around in a circle, as close to a perfect circle as you can. I don't want the ball to speed up.
It's gonna hurt if you.
I don't want the ball to slow down. I just want the ball to go in a circle. Does that make sense? All right, Sean, do you know what you're going to do?
I'm gonna push it lightly to the center, kind of.
Okay, what are you going to do?
Always do it perpendicular to the path, or wherever I want to guide it.
And I'll go poof.
So which way are you going to push it?
Well, it depends on which way it comes.
I know.
Which way are you going to push it?
Exaggerated.
To the
It's
middle.
like
To the
this.
middle.
Oh, which way are you going to push it? Which way are you going to push it? So which way are you going to?
To the side.
Which way are you going to push it? Which way are you going to push it?
I thought you were trying to make it go in a circle.
Oh.
Why are you pushing it to the center?
Oh.
But you'll
So-
see all the force. Centripetal force.
So Macy thinks this isn't going to go in a circle.
Well,
Okay, let's go and see.
All right, so Blake, you got to stand back while I initially launch the ball in, and then once it goes, you guys control it. All right, you guys, everybody ready?
Yes.
All right, here we go.
I did just let you know this.
All right, who failed here?
At the volleyball, you can't just tap it.
Okay, let's go.
All right, okay, ready? Here we go.
Oh.
Too much. It's slowing down. Too strong.
Okay, why is it slowing down? Friction, right? So you actually do have to give it a little bit of a nudge in the direction of motion to account for the fact that it's slowing down a little
I
bit.
got it now.
Does Macy, are you convinced?
yeah,
So,
Oh, go ahead.
yeah.
I saw.
Shit on the kid.
Oop, a little too much.
I think the scroll is tilted because it keeps slowing down.
Yeah, I think it's
speeding
like-
up. I think
it's on
it's
level.
down there.
Yeah.
Yeah.
Still on level.
Or maybe some people are just looking for others. No, because it's doing it in the middle of motion.
Okay.
I think we got it.
All right, you guys got it?
My back hurts.
All right, not bad for a first try. Though there were 3 ringers in the group, so who's seen this before?
Yep.
All right, so in order to get to go in a perfect circle, assuming there's no friction, what way do you have to push?
To the center.
Right to the center, and every single person has to push toward the center in order for this to work. Does that make sense?
Yeah.
And if you do it perfectly, what would you need if you wanted to form a perfect circle?
A lot of people.
A lot of people. How many exactly?
Infinity.
Infinity, right? People. And that's all a circle is. I think you guys knew that from like geometry or calculus or something, right? A circle is just an infinitely sided perfect polygon, right? Right. So you have yeah.
Flatland.
All right, you guys got this?
Yeah.
All right, nice work. All right, stack the books up.
Mr. Bruce, would you like us to put the books back or leave them out for
Actually, yeah, let's leave the books out for 7th hour. Okay, so this is review. Everything that's in thick is actually you saw last year, and everything is in fine print is new for this year. Basically what it was is I was too lazy to recopy all my notes, so I just cut and pasted. All right, so ready? Here we go. First of all, if you're going around a circle, how far is all the way around a circle? What do we call that distance? Circumference. What do you call the amount of time it takes to go around a circle? That's period. So, what's distance divided by time?
Velocity.
Speed, right? So, if you want to know your speed around the circle, it's how far you go divided by the amount of time. Wouldn't you agree?
Yes.
How far you go is the circumference, and the time is the period. So, guess what speed around a circle is?
Circumference divided by
Circumference divided by period, or 2 pi r over t. Do you guys remember that from last year? All right, cool. All right, so that's kind of a neat little tidbit that we'll use in a second. Now, on to more important stuff, the stuff with the bowling ball. You guys messed with the bowling ball, and what was the requirement to make the bowling ball go in a circle? What did you have to do to it?
Give a force to it.
You had to push it toward the center. What direction is that called?
Centripetal force.
It's called the inward direction, right? But there's a fancy name. The centripetal direction. All right, good. And if you push, if there's a net force in the centripetal direction, what happens?
Circular motion starts to increase.
You have a centripetal acceleration. Wouldn't you agree? So centripetal is the name of the direction, not the name of a force. It's the name of the direction. So you can have centripetal acceleration, and forces can be pointing in the centripetal direction, but that is a requirement for uniform circular motion. All right, fine. Oh, that's crazy.
Mixing
Alright.
it up to
Okay. Acceleration occurs in the direction of the change in velocity. So, for example, if velocity 1 started off going to the right and velocity at point 2 was kind of down a little bit, what direction is the change in direction? Or in what direction did the velocity change? Huh, that's interesting. How do you do change mathematically? Final minus initial. So all we have to do this change in velocity is take the final, which is v2, which is kind of down and to the right, minus the initial, which is v1, which is directly to the right. So if you've got down and to the right minus to the right, what do you really have? Down and to the right plus to the left. All right, what do you get when you add those two arrows?
just
Just straight down. Everybody remember how to add vectors? Yes. All right, good. So the change in velocity. So what direction did the particle accelerate in this picture?
down.
Downward, because that's the direction. What way do you accelerate? You accelerate in the direction of the change in velocity, not in the direction of the velocity itself. Does that make sense? Raise your hand if you've seen these vectors before. Like the change in velocity vector before. Is this new? Did you do it last year?
No, it's new.
It's new. Okay. So yeah, this is a really important concept. That's how you get that centripetal acceleration direction. You did it in multi?
I should do it.
Yeah, I think we did. We did multiple grades. We just didn't consider it like the.
Yeah, we had like we get serious velocities. We
We
just
had,
get
like-
serious vectors.
Yeah.
Similar.
Yeah. Sort of.
Similar stuff.
Yeah.
And we used binomials.
So this is a very popular multiple choice question. It'll say something like, okay, your velocity is this way, and then your next velocity is slightly turned from it. What's the direction of the acceleration? And what you have to do is you have to take the final velocity plus negative initial velocity, draw the vector diagram, get the direction of the change in velocity, and that's the direction of the acceleration. Good? All right, cool, next. The average acceleration is also downward in this picture. All right. See, for an object to turn right, it must accelerate to the right. So there it is in car form. Exact same thing. Okay. But what happens if the car continues to accelerate to the right? You get uniform circular motion. As long as your acceleration is neither forward nor backward, but directly perpendicular, what happens to your speed? Stays the same. All right, and then you get this nice circle at a steady speed. All right, you need to know this picture, like know it, like internalize it. Yes.
So it's like described by a car's turning radius.
Yeah. So if you wanted a tighter turning radius, what does the acceleration vector have to be? Bigger. You have to have more acceleration to turn tighter. All right, good. Oh, in order to turn tighter, you need more acceleration, right? So in order to accelerate more, what do you need more of? Force. Net force, right? Okay, good. Next. Notice cars driving in a circle and the acceleration is always towards the center. This acceleration is the centripetal acceleration. All right. Next. In order for anything to go in a circle, the equation for centripetal acceleration is, from last year, v squared over r. Right. This one, you can look up the derivation of v squared over r. I'm not going to do it for you. It's not going to be on the test. But it's not too bad. It's just a geometry thing. All right. Or a calculus thing. Okay, so if instead of writing v, what could we write instead of v? 2 pi over t. So 2 pi r over t, so we could have centripetal acceleration is 2 pi r over t squared over r. Right? What happens if you do that? You get 4 pi squared r over t squared. Raise your hand if you remember that one. Memorize it. If you don't have it memorized, memorize it. And for those in regular last year, memorize this. All right. 4 pi squared r over t squared. Now, you guys know that t and f are related, right?
Yes.
What's the relationship between t and f?
Inverse.
Inverse. So t's 1 over f. So instead of writing 4 pi squared r over t squared, you can substitute... Wow, I did that a weird way. Wow. That's messed up.
Wait, I'm trying to see.
Yeah, that's over r.
You substituted.
Oops.
Okay, wait.
V squared over r. That's supposed to be an r. That's bizarre. I have no idea why I did it like that.
Wait, then what is that? Oh.
It's v squared over r, right?
Oh,
And v is 2 pi rf, which I don't know if you ever did or not. If v is 2 pi r over t,
Yeah.
it must also therefore be 2 pi rf. And then I got 2 r's on top and 1 r on bottom. One of them cancels. So, yeah. That's a weird way to do that. I don't like how I did that. Whatever. Okay, lastly, we know omega. You guys remember I told you to memorize this yesterday? Omega is 2 pi f, right? So if we substitute omega as 2 pi f, this equation just becomes centripetal acceleration is omega squared r. And this actually is the simplest way to write it. Got it? Omega squared r. Or r omega squared. This is the one we're going to use a lot in this class because we deal a lot in radians because it makes the math simpler because you don't have to write 2 pi anymore. Good? So centripetal acceleration is omega squared r. This is actually the easiest one to derive, by the way. All right, so for a given period of rotation, oh wow, Now I want to save that for homework. Okay, let's move on. Okay, if you're accelerating, what do you need? You need, according to Newton's second law, you need a
Force.
net force, right? So, the net force in the centripetal direction equals mass times the acceleration in the centripetal direction. You've all done this before, except for regular. All right. Which means, in general, you have 4 versions of F equals ma. You've got F equals mv squared over r. Or you can do F equals m 4 pi squared r over t squared. Or you can do F equals m 4 pi squared r f squared. Or you can do F equals m r omega squared, which I'll put down here too. M r omega squared. All right. When do you use each one?
Depends on what you're given.
Depends on what you're given, right. Whew. So let's say I give you a question that goes like this. You're driving your car, getting on the highway, and you're driving at a constant 45 miles an hour around the bend.
Bless you.
And I want to know what is the tightest turning radius you can make at that speed. Which version of this equation would you use? Would you use that one, or that one?
when you were given linear velocity? Or
What did I give you? You want to hear it again?
Yeah.
Okay. So you're driving a car around a ramp or around a bend at 45 miles an hour. What's the tightest turning radius you can make? Which version of the equation would you pick? mv squared over r. Good. Yes.
Don't you need to know what M is and force like friction?
I didn't ask you what the answer was. I just asked you which equation you would use. Right? All right. Earth is in a circular, or more or less circular orbit around the sun. It's got a period of 365 days. Oh, what's the radius of its orbit? Which one? Use the second one. Okay, good. Let's see. I'm trying to come up with an example of the third one. You guys get the point? It all depends on the givens which version you're going to use. Okay, good. Moving on. Next, let's say, and no peeking, I'm going to put this picture up. Consider a cone with a frictionless surface on the inside. A block is placed inside the cone, and the whole apparatus is set rotating so the block doesn't slide up or down.
is it like the marble?
Which force am I missing in this picture? So the block is going roundy, 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 roundy in a perfect circle on the inside. It's not sliding up and it's not sliding down. What force am I missing in this picture?
Centripetal force goes.
No, centripetal force doesn't go on the diagram. You're not missing the force.
Frictional force.
Wait, hold on. This block isn't accelerating up or down, right?
Correct.
That means it's staying at the same height, right?
Yeah.
Friction. You forgot friction.
No,
It's
frictionless.
Oh, friction.
It's not missing
It's not missing anything because it'll all cancel out if you.
Wait, hold on. Don't the ups have to balance the downs?
anything.
They
It
do.
does.
Okay, so you're saying that the mg down balances the up component of Fn, right? But if it's not moving anywhere, doesn't the lefts have to balance the rights?
But it's moving
It
in a
will
circle.
if it's fast enough.
No, it's
Yeah.
Doesn't there need to be a force to the right?
No,
no.
because
if you made
you're accelerating inwards.
Inertia.
You're accelerating inwards.
Ah!
You're accelerating inwards.
The force is the one that's moving it, but the block wants to move off at a tangential path to the.
Okay, let me ask you this. Is it going in a circle?
Yes.
Yeah.
So should the forces be balanced?
No.
No! There has to be an unbalanced force to the left in order for this thing to go in a circle. Has to be. Or else it won't go in a circle, right?
Right.
So the picture is correct as drawn. Yes. Well, people think, they look at this picture and they think, oh, if the block's just staying there going in a circle, it's got to be balanced in all directions or else it'll go, well, it is accelerating. It's accelerating in a circle. And it has to be unbalanced toward the center.
Is that like if you were, when you're a kid, you take your marble and you put it in a cup and you...
Right. Yes, exactly. There has to be a force because what happens when that force disappears?
It drops.
The marble goes flying.
Or it goes...
You're right.
out of the cup.
All right. Looking at the free body diagram above, we realize that with just the two forces, the forces vertically are balanced, but not the horizontal ones. They can't be because there has to be an acceleration toward the center. Is the block really accelerating horizontally? Yes. Because it's going in a circle. All right. Centripetal versus angular acceleration. We got, well, three kinds of accelerations to deal with potentially, but we're going to talk about two. What's the difference between alpha and AC? Alpha, okay, so describe alpha?
That's the
What are the units of alpha?
radians.
Radians per second squared. What's the units of centripetal acceleration?
Meters
Per second squared. So that should clue you in on there's a big difference between them. All right, alpha is how quickly you're getting up to speed, right? Or slowing down. All right. Centripetal acceleration is how quickly you're turning in meters per second squared. All right. Let's see. And that's it. All right. So this is a lot of new stuff. This is going to start to get weird and difficult here very, very soon. Because we've got multiple types of acceleration to consider. By the way, there's one more type of acceleration that I didn't put on here. Does anyone know what it is? We've got radians per second squared, that's alpha. We've got the centripetal acceleration, which is the acceleration toward the center. What are we missing? Tangential acceleration. Along the edge. And that's something you never had to deal with last year. We are going to have non-uniform circular motion coming up. What's that mean?
Means it's like the linear velocity is changing.
It means it's going in a circle, but it's speeding up.
That's like planetary.
Yeah. Yes.
Can you explain how like angular acceleration is getting up to speed? What is it?
Rotationally. So you're starting from 0 radians per second and you're going up to 10 radians per second. Or you're starting from 0 RPM and you're going up to 1,000 RPM. Yeah. All right, any more questions? All right, that's it.